I promise that the next time I give a talk here, there will be a second logo. There will be the logo of EGH and the logo of Innopolis. So indeed, it's really great to be able to speak in this seminar, and there was a lot of effort that was put into organizing a regular seminar as a collaboration between Innopolis and our colleagues from Prof. It looks like a simple matter, but in fact it's not that easy to get a collaboration like this going. And it's relatively easy to start things. What's hard is to sustain the rhythm, to have something regular. But I think if we want to have a serious software engineering community in Kazan, then we need to establish this regularity. Otherwise, it just peters out. So in this talk, if I can get this to work, it worked 2 minutes ago. Oh yeah, okay. So this is not the title that was announced, but the content is the same. I want to talk a little bit about the work that I've been doing for a while around the issue of aliasing in programming languages. I've been, for the past 2 years, I've been working on this on and off, and I've had some help from, in particular, Alexandre Kakentev and Sergei Verlev, who were actually at ITMO, which Timur just mentioned. And it's work that is still very much ongoing, so there are a few things that I understand well, and lots of open problems. And so don't take this presentation as the last word. It's really a report on work in progress, and of course it's intended in particular to trigger the interest of any of you who would like to participate in this research. Because I think there's much more potential there than what has been done so far. And obviously I'm thinking of PhD topics and things like that. I think there are several PhD topics possible there. And this is also why I will be quite open about describing what works and what doesn't work. The issues on which I have answers and those which are really open questions. Let me just to check, does anyone know about abstract interpretation, the technique of abstract interpretation of Couzeau and people, and a few other people? Okay, techniques of static analysis. I'll just barely start. Techniques of static analysis of programs. Okay, like the idea that you have a program graph and you can have a fixed point iteration. Does that sound familiar? Okay, good. So we will see some of that. So I'm going to start with a few basics. The first, there's some background. And then I'll give some justification. I'll describe some application. So essentially what I'm presenting is a technique which I call the alias calculus, which makes it possible to compute alias relations. And before, the calculus itself actually comes relatively late in the talk, although I give you an idea of the calculus at the beginning, but I will only give you the actual calculus in part 5. And before that, I'll give you an example, 2 example applications. So it's going to be a bit strange in the sense that I'm going to assume that we have the alias calculus, and in parts 2 and 3, I'm going to show you what we can do with it if we have the alias calculus without actually having introduced it yet. And there's also another application to deadlock analysis, but I found that if I try to present this early, then it's just too many concepts. It goes into another direction. So I'll keep it for the end, and I'm not even sure I will have the time to cover it. So the basic question is very simple. So we have 2 expressions in a program which denote references. Sorry. So I think Yeah, so we have E and F, okay, and they denote, they are references. And a reference denotes an object. Maybe I should use a different symbol here, okay? We have a reference variable somewhere. It could be part of it could be part of other objects. No, I'm not a good drawer, by the way. Don't pay too much attention to my ugly drawing. Pay attention to the semantics. And so the question is, can these references ever denote the same object? Okay? Yeah.
You mentioned program location, and the question is.
No, actually, I didn't. My slide I did, but I didn't mention it yet. But go ahead.
Yes. So, okay, your slide.
That's okay. You're ahead of me, but I asked the question again.
So, what do you mean by program location? So, if this theory is applied to object-oriented paradigm, then, for example, so program location, if we mean runtime execution.
No. Program location means one line in the program, in the source of the program.
Okay, then what is program location for object-oriented programming? So,
Same thing as for non-object oriented.
but when you point to description of some object, it depends on how you call this object, in which context.
Yeah, but the fact that it's object, I understand your point, but the fact that it's object oriented doesn't change anything. So let me bring up a program text. It doesn't really matter what it is. So
actually, we can mechanically transform object-oriented program to procedural program in C, and
no,
then everything.
No, but we don't. That's not even necessary. No. We shouldn't do this. So this is a program location. It's an instruction, and so once in a while, execution is going to reach that point in the program.
Okay, I will ask in another form. If we assume some class, and so for the sake of this task, do I assume that do we fix the overall code of the program? For example, if we assume code for some class, and we use this class object instantiated from this class in different contexts, in different programs. For example, we have two different programs with two main methods. Let's assume Java, for example. And we use one and the same library for both these programs. And this library contains some class description of some class, and we point to some line in this class description. And so it's not obvious that this class description will be context independent.
No, but my definition makes perfect sense. There's no need to have anything more complicated than that. We have a program location, meaning a line like the one that I've identified here. Okay? So this is a program location. Do you agree with this, that this is a program location?
What do you mean by program?
What I mean by program, we have a whole curriculum about this at Innopolis University, and you can register, and the courses start next September.
If we're talking about object-oriented programming, we could have not just a library of classes, not having main procedure.
Sure.
Which you don't have to.
Next,
we quantify over all possible program execution paths.
We don't have program execution if we have on the library.
Well, just to make it simple, can we think of some unique...
Okay, just one at a time, please.
Can we think it in abstract way, as just a unique name of this object?
No, but I haven't even pronounced the word object, which is actually quite strange for me, because usually I don't go very far without pronouncing the word object quite a few times. but I haven't even pronounced the word object. Why objects objects are irrelevant. So okay, let me try to see if we can agree on anything at all. It's okay for me if I spend the rest of the evening covering slide 2.
Okay.
It's perfectly okay. But so, do we kind of agree that we know what a program is?
Okay, let's assume that we have.
No, but yes or no? Who understands? Who thinks he or she has a general understanding of what a program is?
I mean,
okay. Who has no idea what a program is? Okay, good. So program. We can agree on the word program. Now, location. Program is made of text, right? There's a source text. Now, some of these are not meant to be execution location, like a declaration, for example. Where we actually, it's kind of, it's not. Okay, I don't know what's going on. It's actually not. Yeah. So this kind of location is not interesting because it's a declaration or a comment. Okay, but some program locations are instructions. So this is a program location. This is a program location. This is a program location. Then this is in IFO. It's object-oriented, but it doesn't matter. In the program we have, and it could be a library. Who cares? I mean, there's just instructions in the program text. So can we agree on what a program location is in the source data? I should have said the source program location. Okay.
So excuse me.
Yeah.
Am I correct in understanding that the program location is ultimately defined by name of the file and line?
If you like. Yeah.
Thank you.
Okay. Okay. So can we agree that we have some kind of understanding, which varies a bit with the programming language, of the notion of expression? An expression being some kind of construct that denotes a value. Like, for example, here, I will pick this at random, right? But here we have active, we have first element. These are expressions. Actually, they're very simple expressions that just variables. Okay, so we have, for example, first element is an expression, and active is an expression. Now, because they are expressions, they are elements of the program text that denote certain values. These values can be references, as in my picture, right? Now, these values could be integers, they could be booleans, but they can also be references. It doesn't have to be object-oriented, it could be in C. In C, when I say reference, it could be pointer. There's no difference between reference and pointer. Address, if it's machine code, we talk of address. And so the question is it possible that when an execution reaches position P, which it can do many times, or not at all, but if execution reaches position P, is it possible that ENF can be attached to the same object? So attached is the terminology that I like to use to say that a reference is attached to, meaning it denotes a certain object.
So this makes more sense because different executions may reach one and the same positions.
Absolutely. Absolutely. So, actually, I have a formal definition of this somewhere. I don't think I have the slide here. No, I don't. But this. If I had known you would have been asking such pointed questions, I would have prepared it. Maybe if I have a couple of minutes, I will locate that particular that particular slide. But let's just use the informal interpretation here. We're asking a question: can it ever be the case that in some execution, ENF will be attached to the same object? And so in such a case, we say that E and F are alias. So it's important to note, as you have already pointed out, that we really mean potentially alias. Now, technically people talk about may alias and must alias. Must alias is a relation that holds when it's always the case that E and F at that particular program location are pointing to the same object. May alias is the relation I'm interested in this discussion, and it's the one that holds if it can be the case that in some execution E and F can be alias. And that's the issue that we will be studying. Okay?
So, how it's called when E and F are never aliased?
Well, there's no specific name, but it's may alias. Because if you have the answer to one, you have the answer to the other. And in fact, no, but this is also a good question, because usually this is what we're interested in. Very often we're interested in the guarantee that E and F will never be the same, because then we can, for example, perform some optimizations in the compiler, or we can have certain proofs in verification. So indeed, may alias is not that interesting in itself. May alias is interesting for its complement. Because if what we want to prove is that E and F may not be aliased. But for that we have to compute the may alias relation. And I'll come back to that your question because it was. So I think I'll skip this, yeah. Okay. So as an example of alias analysis, this is very informal, but this is the kind of thing that the alias calculus can do for us. Assume that we have these two linked list structures, with yellow cells that contain objects, or more precisely, pointers to objects, and then we have this other list here. So basically, what we are going to be able to, So let's assume that there's only one operation, which is, as illustrated here, to add an element at the end. Okay, let me show it again. We want to add an element at the end. Because in order to prove anything, we need to know what the possible operations are. So here we would have the typical operations: extend, the one I just illustrated, add an element at the end, and then we will have a deletion, and so on. And so what we're going to be able to prove with the mechanism that I show is that if x is not equal to y, so if x actually may never be alias to y, then, speaking informally, no yellow cell will ever be alias to a green cell, and no cell can be both yellow and green. That is to say, nothing reachable from x can also be reached from y. The blue cells and red cells are also different. And if we don't know that x is not equal to y, then we cannot prove that. So you can see the proof. If we have the assumption x not equal to y, then we can prove the property. If not, we cannot. This is the kind of thing that we'll be able to do. So this is actually,
I'm sorry, I didn't get why blue and red cells never mix.
Assuming they are not okay, forget about the blue and red ones. What's important is the yellow and green. Yeah. You're right. The point is that we assume that blue and red cells are allocated each time rather than existing cells. So if they are existing cells, then they could indeed be shared. I should just have ignored that part. Okay, so this is what I'll talk about in the second part of the talk. I'll explain the rules in detail, but I want to give you an idea of the style of the alias calculus, so that you know what we're aiming at. So we're going to get a calculus that always has properties of this form, and what it means when we have this notation here, it means that we take an existing alias relation and we look at the resulting alias relation when we apply a certain instruction. So A is an alias relation. Sorry, this is a little bit, I hope you can see the left-hand side. It's a little bit cut off by the projector. So in any case, the left column is always A on this slide. So A is an alias relation. It basically tells us what could be alias to what. So it's a set of pairs, like any relation. And with this little symbol, which I'm just introducing for this purpose, which means, which I'm going to read as alias, we execute an instruction afterwards, and we get the new alias relation after executing that instruction. So we can look at the first two because they are trivial, but they make it possible to understand what we're talking about. Let's assume that I have a certain alias relation A here, which says X could be alias to Y, Z could be alias to T, Z could also be alias to X, and so on. That's what an alias relation tells us. It's a May alias relation. And now I'm going to execute either instruction P or instruction Q. Now, in practice, it's going to be if something, then P else Q, but let's ignore the if part. So we execute either P or Q. Then you can see what it says. It says that as a result, we are going to get any pair, any aliasing that results from executing P, starting with A, plus, that's the union, any pair that results from executing Q, starting with A. Yeah.
So we assume that if part doesn't introduce any, is forbidden from introducing any aliases. There are no assignments in if
Oh, you mean side effects? Side effects.
Yeah.
Well, there's not even an if part here, but yeah. And so the next one, I'll come back to the others later. Let me just explain the first two. The next one says, if I start with an alias relation A and execute P then Q, what am I going to get? Well, I'm going to get the aliasings that result from executing Q, starting with the alias relation that results from executing P, starting with the alias relation A. Okay? And so the others are less obvious, and we're going to come back to them, but what I want you to understand is the kind of style, the general context in which we are working here. Okay? So let's assume that we have this alias calculus. Okay? Because I'm going to introduce it later on. Let's just assume that we have it. What could we do with it? And why is it useful? Well, here are some applications. The next one I'm not going to talk about at all, and it's not my field. I don't know that. I mean, I know what compile is, but we have not applied this theory to compiler optimization. But things like reasoning about object-oriented programs, frame inference, and deadlock detection if I have the time at the end. So let me give you some examples. Okay, who does not know what this notation means? Be honest. Okay. These are so-called, so who knows and can explain? Ah, this is where, because then I can ask any one of the others. Right? This is where we call your bluff. Yeah.
So we apply some predicate to. We say that E and S are in some relation which is explained by predicate.
Right. So this, okay, this is known as a precondition, the part before, and the part after is known as a postcondition. And when we write P, A, Q, this is known as a core triple. Okay. What we're saying is, we know that whenever we execute A, so A is an instruction or a piece of a program, starting in a state in which P is satisfied, then we are certain to have a final state in which Q is satisfied. Okay? So, so there's a whole theory which gives the rules in this style for every kind of instruction in a programming language, and this is kind of the central one, which says this. Assume that I have a certain property P, and I want to make sure that at the end, P holds of the variable x. And the program in this case is just the assignment x receives E. Well, for that to be the case, it must be that P holds before, but it holds of E. Okay? So whatever I want to have as a property of x at the end must be a property of E at the beginning. And again, if you're going to ask the same question, we assume that there's no side effect in E. Because if there's a side effect in E, everything breaks down, but then actually we can still handle it, because we basically said this is two instructions. One which does the modification, and one which does the assignment. Okay, so this looks very nicely. For example, let's assume that my postcondition, I'm using Eiffel syntax here, so ensure is a postcondition and require is a precondition, right? Ensure is what comes at the end, here, and require is what comes at the beginning. So my postcondition is that y is going to be less than 3, and we're talking about integers. And my precondition is that y plus y is less than 3. So this important instruction, by the way, is going to be this one, interesting. So here, ignore the x receives whatever for the moment. Okay. I want to prove this. It's trivial. It's trivial, but let's do it mechanically, the way a program proves it as an automatic theory program proof. So you see I have y of 3 is like p of y. And so I'm going to move it up. This is the way the assignment rule works, and it gives us y plus 1 less than 3. Right? Which is exactly this mechanism, p of y, and here p of y plus 1. Okay? Now, and so if we didn't have the externality here, we would stop here. Yeah? Because obviously, that's what we want at the beginning, so everything's fine. But now let's assume that we do have this line. And we say, okay, here we have an assignment to what? We have an assignment to x. And x doesn't even appear here. Sorry, I messed up my animation. So we can just move the y plus 1 less than 3 because there's no okay, the property does not talk about y in this case. Okay? So this works nicely because we have an instruction here which involves something else than 1. So it doesn't bother us. It would play a role if we were trying to prove another property that involves x. But since we're talking about a property of y, it's completely irrelevant. Okay? So now let's try to transpose this nice classic reasoning in the Hoare style to not integers anymore, but references. And then the whole civilization and the world as we know it is going to break down. So I'm assuming that I have x.set A of C. So, you know, I'm kind of a bigot of object-oriented programming. I'm very dogmatic about object-oriented programming. You know, if people use Java or C++, they're going to write something like this, x.A receives C. But of course, this is very bad because it contains information hiding and so on. So I'm writing x.set A of C, and you see what set A does. X denotes an object that has a field A, and it's going to change the A field. So here's the original picture. X is attached to an object that has an A field. A should actually, I don't know what happened to my slide, maybe it's the projection, but A should be this field here, and A is attached to, the A field is attached to some object, which is also known as B. And then we have C here. So, and this is what set A does, right? It changes the A field to, in this case, C. Okay? So let's try to reason the same way. Let's assume that the post condition says that x.A is equal to C. Yes, this is going to work because we perform the standard Hoare transformation. But now let's assume that what we want to check at the end, the post condition is y dot a equals b. So it's very similar to what we were doing with integers before. And so we say here, okay, there's no y here. It's only x. So as we were doing before with integers, we can just push this thing through. It doesn't change. And so we get y dot a equals b. And is this true?
Not necessarily.
Not necessarily. That's the right answer. Yes is the wrong answer. No is also a wrong answer. Not necessarily is the correct answer. And why would it not hold?
Yeah, when we have Alias.
Exactly. Y and x could actually be the same thing. Okay? So now, you could say we have to, so this makes reasoning about programs with references, pointers, very difficult. Because you never quite know what you're talking about. Now, you could say we avoid AUC. We don't use it at all because it's bad, it's messy, but we cannot. We need references, and as soon as we have references, we need AUC. And in fact, I would contend that it's inevitable. Now, let's assume this following situation. Someone tells you, well, okay, on Saturday, someone tells you I'm in Kazan, and it's very warm here. Okay. And then you hear that in the capital of Tatarstan, the temperature has dropped by 20 degrees. And you ask again for the next day, is it warm in Kazan? Well, nothing has changed affecting Kazan. But it's exactly this situation, because we are talking about the capital of Tatarstan, and that is an alias for Kazan. Okay? So I think this, to me, this is an opinion, it's more philosophy, it doesn't matter so much for the rest of the discussion, but to me, aliasing is not just something dirty that programmers do, you know, like go-tos or things like that. It's because you know, there are people who say this. They say aliasing and references and so on, that's the go-to of data structures. But I don't think we can just get away like this, because aliasing is a result of the human ability to give names to things and to give several names to the same thing. And we do this all the time, and not just in programming. So we have to find ways to reason about this. Okay, this I think I'll come back to it. So let me give you another example of application. I'll come back to the part that I've seen. There's a very important problem in verification, which is the so-called frame analysis problem, framing problem, which was first described. I don't think I brought the citation here. No, I did not. There's a very nice citation in a paper of 1964, so 50 years ago, by John McCarthy, the creator of Lisp, who explained very well what AUC is about. But I'm going to illustrate it in a more technical context. No, sorry, not AUC, framing. So we have a little class account, and it has things like deposit. So the account has a holder, it has a balance, kind of standard object-oriented example. You can see here that the deposit has a certain implementation. The implementation doesn't matter that much. And the post condition is that if I deposit a certain amount of money, the balance has been increased by that amount. And so here's what we can do. So we have the holder, we have the balance, and then we deposit to handle rubles. Now the original balance was B. So here I'm using this Eiffel construct check, which is like the things in braces before, you know, now the post condition. So here I'm pretty sure that the balance is equal to the old balance, the B was the old balance plus a handle, because that's what the specification says. So there's lots of things to say about that part of program verification, but that's not what we're concerned about here. What we are asking ourselves is, has the holder changed? All that we've done is a deposit. And all that the specification of the deposit says is the balance is the old balance plus the amount. So normally when you deposit money into the account, it shouldn't change the owner of the account. That would be, I mean, if you're the mafia, you probably want to have things to do things like this, right? It would be very nice to hack the implementation of deposit so that when the customer deposits a certain amount, like 123 rubles, 0.75, it actually changes the owner to some mafia guy somewhere, changes the holder. But that's not the idea. However, with this specification, we've not said this, right? We have only said the balance will be changed as pointed out here. We have said nothing about the fact that the holder doesn't change. And we could have lots of other things. You know, apart from the holder, we could have the number of the account, we could have the name of the bank, and bank accounts have lots and lots of problems. And here, it is absolutely impossible to guarantee that we can still prove that the holder has not changed and that the number of the account has not changed. So of course we could say this is valid. So we're going to make it part of the specification of the routine. We're going to say holder equals old holder. And then we say for this particular example. But of course, what about everything else? And it's not, so we are going to have to, whenever we specify something, we're going to say, okay, this is the interesting part. The deposit changes the balance, and on top of that, the holder doesn't change, the bank name doesn't change, the account number doesn't change, the address of the owner doesn't change, and so on. And so our specifications are going to be huge, and most of what we write is going to be completely uninteresting. It's going to be things of the form, blah blah equals all blah blah, for all kinds of blah blah. But that's not the worst. The worst is that if we add something new, no, we hadn't thought about it before, but now we are saying an account also has a branch. You know, it's Bancasia, but we also want to record in the account what is the local branch where the account is being managed. Okay? So fine, we just had this, but then for all of the existing contracts, all these existing specifications, we're going to have to say branch equals all branch. So not only do we have complex and very verbose specifications, but we keep changing them all the time, each time we add something. So it's not workable. So, okay, this I'm going to skip. Now, people have been aware of this problem for a long time, and the standard solution is to have a special clause which is sometimes called a modifies clause. The keyword changes. But the standard keyword is modify, so we are going to write something like, I'm using the keyword only here. So we are going to say only balance, which is just an abbreviation for everything else doesn't change. Branch equals all branch, number equals all number, and so on. But you're only going to list what can change, and you're never going to list exhaustively what doesn't change. That is, it's implicitly anything that is not named here does not change. So this is the basic answer to this question, but it's not that it's not the final answer. One minor little detail with modifies clauses is that you cannot write them in practice. It's impossible. So let me give you an example. Let's assume that we have this routine here, and so what it does is that it goes through the list, to this list, and you can say that it stops until I equals n. N is one of the arguments. So when it reaches the nth element, it's going to replace its value. So for example, if n equals 4, we are going to change that value here. Okay, this is what the code on the left does, until I equals n, we go to the next element, and then we change the value to x. So let's assume we write the modifies clause. Well, what can it modify? It can modify first dot item, it can modify first dot right dot item, first dot right dot right dot item, first dot right dot right dot item, and so on. So it's infinite. So we have a problem. We cannot write it because we have to take some conventions as to in order to write these modifies clauses. So the first thing that we're going to do is that we are not going to write modifies clauses. This is more like a programming language decision. We are going to say anything that is not named in the post condition is not modified as a language convention. And so no operation may affect a system property unless its contract, meaning in this case its post condition, explicitly mentions that property or some part of it. So for example, if we say here, ensure C equals A, then it means it can only modify C and A, because C and A are named, and anything that is not named, well, it should say B, B shouldn't change. But then, this is still, we should still verify that the program is correct. So, that is, if the program verification is going to be meaningful at all, then of course the specifications should be correct, should apply to the code. And for this, we're going to need the change calculus. So here's the change calculus. It tells us what can change as a result of any instruction. So underline here means what can change. So here are the rules, they're very simple. The really interesting one is this one here for codes. The others are kind of trivial. Well, except that there is a surprise for the last one. So again, what this means, I understand that you might be a bit lost at this point, but in fact it's very, very simple, and I hope you understand this change calculus. So what this says is, what can the execution of P followed by the execution of Q change? Well, it's whatever P changes and whatever Q can change. Okay? What is it going to be for then P else Q n? Okay, again, we ignore the if part. So then P else Q is kind of either execute P or execute Q. It's kind of non-deterministic choice. And of course, in practice, it's going to be if C, then P else Q, but C doesn't play a role, especially if it doesn't have a side effect, so we ignore. So what do you think is going to be here? Sorry?
P union Q?
Same thing, absolutely, the same as the first. Yeah. Loop, well, in this case, it's going to be a fixed point. Yeah, it's at this level at least, it's an infinite union. So by P, I mean one execution. By P squared, I mean two executions. P then P. P cubed is P then P then P, and so on. It's the infinite union. So for a call, it's actually quite simple because. So, yeah, of course, in programming languages, we don't write a keyword call. We just write R of L, but for clarity, I use the explicit keyword call. So L is the actual arguments, and so what this means is, if this thing between bars is the body of the routine, so we take the body of the routine, it can change some things, and then we do a substitution. This is a substitution of the actual arguments for the formal arguments. R has some formal arguments f, and we substitute the actual arguments for the formal arguments. Is that clear? I mean, the call changes what the routine actually does, but it does it for the actual arguments rather than the formal ones.
So we don't distinguish by ref and by val.
Yes.
We assume call by value.
By ref, I guess. Otherwise they wouldn't change.
So, sorry, say it again?
We assume by ref call, I guess.
No, it's called by value, but of course references are, I mean, the values can be references. So yeah, definitely called by values. Now, so far there's no object-oriented construct, but now comes the core object-oriented construct, and we say call R, but call it on X. Okay, so this is where aliasing comes in. You might have been wondering why I was talking about framing and so on. Well, it's because we need aliasing. This is an ad hoc notation, which I should actually relate to the previous notation with the double greater than, but this means the aliases of X. So let me, I don't think I have a picture, no. Let me draw the picture. So, yeah, to explain this rule. So we have X, which is a reference to a certain object, and we do X dot R. Ignore the arguments, it's R dot L, but this is the same as before, substitution of actual formals. But, so this is this object O, okay? And then we execute R on this. And so R is going to make some changes. Maybe it changes this particular reference, or pointer, and so on. And so we could say what X dot R changes is X dot whatever R changes. So the dot means, the dot has to be generalized to lists, right? So when we have something like X dot the list ABC, this means the list X dot A, X dot B, X dot C. That's what this dot means here. So, you know, it could be, as a first attempt, which is wrong, we could say what X dot R changes. I have to remember not to write too much on the left because I have much more space here, but you can see, sorry. What we could say that what X dot R changes is X prefix to everything that R changes. Yeah.
Regarding screen space, may I suggest moving the bar from right to left? So
you're a real engineer.
Yeah, no, I mean taskbar, Windows bar with start button. This gray line on the right to the
sure.
left.
I know. Well, no, but this. Okay. Yeah. Okay, sorry, I should have done that. Well, I can if I really want to do that. Where is it? It's auto hide, okay. I think that's what you want, right?
Well, that works too.
Okay, so our bar here is what can change as a result of the execution of R. So you could say what changes as a result of the execution of X dot R is everything that can change as a result of R prefixed by X. So if this is A is changed, and so X dot A is changed. If this is also changed, let's say B, then X dot B is changed, and so on. So this is true, but it's not true, it's not complete. Sound, but it's not complete, because if we have anything that is aliased to X, say Y, it also changes. Okay? And so that's why in the rule, we don't say x dot the result of the call, but x aliased, all the aliases of x. And so again, we generalize the dot so that everything to the left of the dot can be combined with everything to the right of the dot. So this is the connection between the alias and the change calculus, and that's one of the major applications of the alias calculus, because as a result of this rule, if we have the alias calculus, meaning the ability to compute this, then we can do the frame computation as well. We can. Okay? Now the last rule is, it's in a way trivial, but there's a little surprise. And the result is this. If I don't show you this, and I ask you what can be changed by the assignment T receives S, if you're very smart, so I'm sure you're not going to fall into that pitfall, but someone who is not as smart as you are, as we are, okay, let's put that all together in the same boat. If someone who is less smart than we are would say, well, of course, it's T that can be changed. This is an assignment, all that it changes is T. But in fact, again, drawing a picture, let's assume that we have T, which points to something, and then we have S, which points to something else, or it could be the same, doesn't matter, and then we do T receives S, okay? So only T changes. But now we are talking about expressions in the program. So let's assume that we have an expression that, for example, U points to this, and here A is actually, no, I'm sorry,
It's a part of an object.
U is attached to this object, and here the field A was actually aliased to T. So U in this picture, U dot A is alias to T. Well, because we're changing T, U dot A dot T, U dot A dot T also changes.
There is no U dot A dot T.
U dot A,
Well, you should point A to T, I guess.
sorry, you're right. Okay, it's what I had done first.
T should be a part of an object,
Yeah.
which is aliased.
Okay, let me do it again. You're right. So we have T, we have S.
S would be any.
Okay, S doesn't matter that much, and then we have U, and U is actually an alias to the current object. That's what it is. Okay? And so what's going to change as a result of T receives S is T, but also U dot T. Okay, and that's what the rule says. Aliases of current is like this. It's the iPhone notation for this or self or in small talk and so on. So that is the assignment rule. Okay. So how do we verify frame properties? Let's assume that we have this convention that I mentioned, that we have modifies clauses. It doesn't matter that much whether the modifies clauses are implicit or explicit. Remember I said we could explicitly say only or modifies, or we could have this convention that anything that is not explicitly mentioned in the post condition is considered to be unchanged, to be outside of the modifies clause. So let's assume that we do have a modifies clause, implicit or explicit. I call it modified clause. So PM is the list of expressions that appear in this modifies clause. P is the program. P underline here, that's the real stuff. And it's the actual semantics. It's what the program can actually change. So we assume that we have some supreme intelligence somewhere out there which knows what the program can change in all of its possible executions, or in any of its possible executions. So P underlined is the truth. Okay? And of course, we don't know the truth, we can only try to compute the truth. So for example, we can write a modified clause, which says, I, the programmer, say that only A, B, and C can change, and nothing else. And then we can have a change analysis, which actually tells us what actually can change. That's an automatic tool. So let me ask you a question. Can we write a sound and complete change analysis? That is to say, can we, I, or you, who are obviously much smarter than I am, can either of us, the smartest person in the room, write a perfect change analysis that will tell us exactly what expressions can change? No? Okay, let's do it the democratic way. Who says yes?
I think it's possible, but it's equivalent to half problem. Yeah, it might never stop and give us result.
So is that a yes or a no?
It's yes, but it's
no. There's no yes, but it's.
We can program change analysis.
Okay, we'll give you 10 minutes so you can step. You can go out and please write it and come back with the result if you say yes. No, okay. No, I'm just. There's no yes, but there's only two possible answers: yes or no. So I come from Switzerland. In Switzerland, people vote on absolutely everything. Every 6 weeks they go to vote on whether to paint the bridge in blue or in dark blue or light blue. So we do it democratically. So who thinks yes, it's possible? Okay, who thinks no? And the others are toasted. Cows. Who is a cow? Kto jest toast? Certainly. Okay, so, well, the answer is no, but I think when you said yes, you really meant no. I understand this, because you gave the right answer, because in fact, it's undecidable. Yes. So it's impossible, which is, I think, what you were saying, when you, so, no, if you say it's the equivalent to the halting problem, and you say yes, then I'm really, really interested, because I want to see your answer to the halting problem. Please, I mean, I hire you on the spot. Double your salary. Yeah, it's undecidable. Now, there is a kind of general result in computer science which can be stated in an informal way as all interesting problems in computer science are undecidable. Now, interesting is not a formal notion, but actually there's a formal form of this theorem. I think it's called Rice's theorem, which basically says this. So this is an interesting problem, and hence it's undecidable. But this is very important, and this also applies to Alias analysis in general. Here I'm talking about change analysis, but for Alias analysis that's true. We cannot have an analysis that is sound and complete. So what does it mean, sound and complete? Sound means, in this case, that if a program can change a certain expression, then the analysis will tell us. So it's never going to miss any case, which is what we want, right? Soundness. Complete would be that if the analysis tells us that something can be changed, then there's some program execution somewhere that is going to change it. You understand? It's sound and complete, right? So, and we can, what's undecidable is to write an analysis that is both sound and complete. Well, what's impossible is to write an analysis that is sound and complete and always gives us a result, because we could also pretend and say, oh, it's just that my machine is too slow, so just wait another 5 minutes to get the answer. But okay, that's cheating. It doesn't. And so we can have it complete, but it's not going to be sound. In some cases, it will tell us this is not changed, but in fact, it could be changed, or it could be the other way around. And of course, if we have to choose, we need soundness. Obviously, for program proving, we need soundness. So, and then as all such problems, it becomes a practical problem, an engineering problem. We know that we cannot have a perfect answer, But we want an answer that comes quickly, and that we want an answer that is not too imprecise. By imprecise, I mean telling us that some things can change where in fact they cannot change. So, you know, because there's a very easy way to have a sound analysis, which is to say everything can change. Well, that's not complete, but it's sound. It's true, right? It's never going to tell us that something cannot change if it can, but that's completely useless. And what we would like is the exact one, but we cannot have it, so we are going to tolerate some imprecision, but then it becomes an engineering problem of how much imprecision we are willing to tolerate, and we try to have as little as possible. Okay? And so, we have this, these elements here, and after that, what we are, so what we can do, and what we did with Alexander Kaktienkov is, well, we verify, we run the change analysis, and now we verify the modifiers clause. We verify that PA is a subset of PM. That is to say, everything that is mentioned in PM, everything that the programmer has written can change. I'm sorry, everything that can change the other way around, everything that can change has been listed. Now, if the programmer has said the holder can change, and it doesn't, well, it's a pity, but it's not really a bug. It's just being too careful. Okay, it's an imprecision. Now, but on the other hand, how do we know that our change analysis is correct? Okay? Well, we don't. It's just a theory that we have. So the real thing is P envelope. The real what can actually change. And so, as a consequence, if the modifiers clause are sound, then P is in PA, P is in PM. So that's what we do. So, if you want to go, Alexander Kaktienkov ran this, actually programmed all this on the library. Now, the library is called Innopolis Plus. It's actually, it was an experiment. It's not a, so there's an actual library called Innopolis, which is very important for Info programming. It's like Java connections or C# connections. It's stacks and queues and arrays and files and so on. It's the basic stuff. But it's not appropriate for verification. It has contracts, but they're not formal enough. So another then PhD student at ETH, Nadia Polikarpova, and all these are Russian names, Russian people actually who have been working on this. She wrote for her thesis this Innopolis Plus library for some experiments. But it was interesting to use because it was very precisely specified. It was meant for formal verification. So it had all the modifiers clauses. And that was, of course, interesting. So what Alexander did was to look at the modifiers clauses, and he performed the change analysis which uses the Alias analysis. And so that makes it possible to obtain inferred modifiers clauses. These are the bottom left. They're the ones that Nadia wrote in the library. Those are the top right. They're the ones that Alexander computed as a result of Alias and change analysis. Now, there's a little problem, which is a technical problem. It makes things a bit more messy than we would like. Is that here they are not exactly the same thing. These ones are on model queries. These are attributes. I'm not going to explain this now. Just so that you know there is a technical problem. So we need to adapt these manually so that they are comparable as a result. And then we can find out, and then we go back to the previous slide, we check that all the things that can actually change as a result of the analysis are also listed in the modifiers clauses. Okay? So this is what the experiment ran. It's a library of something like 30 classes. So it's not huge, but it's also not ridiculous. Okay? And also it's relatively difficult stuff because it's all this pointer manipulation, linked list, and circular list, and so on. So it's far from trivial. And so the results are these. You can see that, as I said, it's not ridiculous. It's 600 so there are some technical issues between this model, this manner of models to code. We found that 1% were kind of overprotective. They said there was a modifiers clause, which was actually not needed. It said X could be modified and X could never be modified. So, as I said, it's not a bug, but it's a nuisance. Then, there are cases which are a bit tricky. For example, we found some missing modifiers clauses, but that's because there's code that could not be executed. You know, you shouldn't have this in code, unreachable code, but it happens because of the evolution of the software and so on. So if you say modifies X only, and the code can modify Y, it's a bug, except that if it's part of the code that, because then we looked to see exactly what it was, case by case, and if we find that this code can never be executed, well, it's not really a bug. There's inaccurate array representation. This is a technical problem that we have. Now, this one is interesting, and it raises the problem of what exactly do we mean by change. Assume that we have some piece of code on a data structure, for example, a linked list. On our linked list, we have, on our list in general, we have a notion of cursor. So there is a kind of current position, and then you can move the cursor back and forth. Let's assume that we say, okay, here's the cursor position, we record it somewhere, and then we go elsewhere, remove the cursor, do some work on these other elements, and then at the end, we restore the cursor to its initial position. Well, the Alias analysis, the change analysis is going to tell us you modify the cursor, which is true. But it's not in the modifies clause because, in fact, at the end of the routine, it's equal to the old one. Cursor equals old cursor. We changed it and we moved it back. So we could say in such a case, it's not really a bug, and we are going to have this problem anyway. But we were very proud, and the author of the library, Meyer, was very upset that we found, because she had written the, so we fought a lot about it. She said it was not right, but I think in the end, initially we had identified more, and then in talking to her, we realized that many of them were artificial, did not exactly exist. But in the end, we found 7 missing clauses, that is to say 7 cases of things that were modified but not listed in the modified clause. Now it turns out that, to boost a little bit about some other aspects of our research, we have a very good automatic testing framework called Autotest. And in the meantime, between the time we started working with the library and the time we performed this analysis, Autotest had found 5 of these bugs, and they had been fixed. But there remained 2 that that had not been found, so we could claim victory, except that it's us against us, right? I think it's very interesting to show that even in a very carefully written library, there can still be cases like that, and the analysis can find it. This library was interesting as an example, again, because it had been written very carefully for specification. Okay, so that's the application to framing. Okay, I think I'm going to skip the part on negative variables for the moment, because I also don't want to keep you for too long. I'm going now to introduce the Alias calculus. It uses negative variables, but I'll kind of finesse my way over this, and then if you want the details on the negative variables, I'll give them, but I've already been talking for more than an hour, and I should let you go home and enjoy the weekend at night. So, this is what I already said. These are what we want for automatic Alias analysis: soundness, precision. Although we know that we cannot. So for soundness, we want perfect soundness. At least. Well, this is also debatable. We'll see in practice. For precision, it's more of an engineering trade-off. We want as much precision as we And then we want to cover the entire programming language. Modern programming language like IFO has lots and lots of constructs. So we cannot just say it works for a small subset of the language. And we ignore exception handling. We ignore closures. We ignore recursion. Then the problem becomes much easier, but the analysis is useless. So that's really the big difficulty of this kind of work, is that it's kind of all or nothing. If you cannot cover the entire programming language with all the crazy mechanisms that modern programming languages have, it's not very useful. Actually, this is, the realism, I mean a real programming language like Java or IFO, not a toy programming language, and a completeness means covering the entire programming language. And also, it should be efficient, where you don't want to have to wait 2 days to perform Alias analysis. Okay, so now I'll go very quickly over the actual calculus. What we're looking at is Alias relations. What's an Alias relation? It's a relation. So Alias relations are symmetric and irreflexive. They're not transitive. So you look at this case here. If C, then X receives Y, else Y receives Z. So the first one will alias X to Y, the second one will alias Y to Z. But the conditional is not going to alias X to Z as a result. So the presence of conditionals is the reason why we don't have transitivity, but we have symmetry and we have irreflexivity as a convention. Oh, actually, this is a slide I was missing earlier. It's the formal definition of alias relation. I don't have the time to go into this. I can answer it if there's any question. And so this is the kind of things we're dealing with. A, alias P. This is the aliasing relation resulting from executing P from initial state in which the aliasing relation is A. And, okay. Okay. So here's the calculus again. The first one is kind of stupid. I should have removed it. If you do nothing, it doesn't change. The skip is the instruction. It's a no-op, right? So, yeah. So this one we've seen already, the first two. Then forget X. Forget X is, in my mini language, I'm writing this for a kind of mini language which is a subset of, which is, common metaphor, so to speak, for all object-oriented languages. Modern. So forget X, this is X receives no. In Java, X receives void in IFO, which is not like a normal assignment. It's a special assignment, so that's why I treat it like a separate instruction. And so what does it say here? It says that if I do forget X, then we get A plus anything that involves X. So the minus here is like remove everything that starts with X. It's a generalized set difference. What's also interesting is that create, which is like a new in Java, has the same effect. Because if we do a new on X, it's like removing X from all the relations that we had before, since it gets allocated in new. So I think it's fun to see that forget, setting to void, to null, and the new have the same effect from the viewpoint of aliasing. Let me ignore cut, loop. So it's the infinite union, and of course we have to see whether there's a fixed point. I don't have the time to go into this. It's the effect of executing P, the 0 term. So you can see what I'm doing here. I mean, I'm kind of abstracting from the loop constructs of programming languages. In particular, of course, we always have a termination condition, but it doesn't matter. It has no effect. So that's why I'm just writing it while. I'm just writing a loop Pn instead of while, instead of until, and so on, because these parts don't have any effect on the alias calculus. So it's like executing A, not at all, like a skip, or once, or twice, or 3 times, and so on, and we take the union. Okay. And then these are the rules for calls. It would take me another 10 minutes, 10, 15 minutes to explain the details. So I won't, unless there's a question about it. And then we have the assignment rule. That's probably the last one I will cover in detail. So what is the effect? I don't know why I called it R here. It should be A, like in bifocal compatibility. Sorry. It's the same as A before. Well, it's not as trivial as one could expect. What is the effect of the assignment T receives S starting with an Alias relation R? Well, the simple, so let me, rather than explain the details of the rule which you can find in the papers, let me give you an example of why it is not absolutely trivial. Okay, let me ask you a question, or using the same notations. T receives S. Okay. If it's Java, you remove the code, right? T equals S, right? T and S are references. So let me ask you the following question, and again, I'm going to do it the Swiss way, right? And here, you're not going to be permitted not to answer. Everyone has to raise his or her hand once, exactly once, because that's another way of cheating to answer both yes and no. So I'm going to be really, really tough this time. So the question is this: is it always true that as a result of this assignment, T and S will be aliased? They're both references. Is it always true that in the resulting alias relation, we are going to have the pair T, S? So I'll let you think about it for a second. Don't say anything. Just think. You have 10 seconds more to think. Okay, so now we take the vote. Who thinks it is not always true? 1, 2, 3, 4, 7. Who thinks it's always true? You have to raise your hand now. Everyone else has to raise his hand, right? Come on. Okay. Okay, well, some of you are cheating and not really answering. I don't like that at all. So those who think it is not always true, why? You need a counterexample, right? You cannot just say, well, yeah, this guy is devious and nasty and so on, so if he's asking the question and it seems so obvious that it's true, he must be thinking of something. So that's not good enough. If you say, no, it's not always true, I want a justification.
Okay, trivial example is when S is effectively null, yes, and we go back to rule erase T.
Well, okay, but that's
trivial.
No, but it's still T and S actually they're both going to be no, so you can say they're used to each other. So it's not good enough. No, they are no, that doesn't work. You are going to be very upset at me, but also at yourself when I give you the answer. Right? So think hard, because it's going to be very bad for your self-esteem when I give you the answer. So I will give you the answer now. And then you're going to be so upset. I mean, it's going to spoil your entire weekend. So are you really upset at me? No? Are you upset at yourself?
With a lot of variables, of course.
Yeah, but it's expressions, right? So T, as after this expression, this instruction, T is not going to be aliased to T dot A. because now T, well, this was the old T of A, so we change this. And then we might have an A here, but T is not alias to T dot A, except if this thing, in a special case in which is cycling. Okay? So, now, you don't have to feel bad, okay? There's really nothing wrong with you. And I have made so many mistakes in looking at these things, and it's very, very tricky. It's devious. It's straszne.
Yeah. But still.
So this is now I'm not going to explain the details of the rule because of the time, but I believe this rule to be sound. Actually, it's been proved to be sound based on an appropriate semantic model. So I know it's sound, but you can believe me that we didn't get this version of the rule the first time around, or the second time around, or the third time around. So, to conclude, I said that it's not possible to get a calculus that would be both sound and complete, so it has to be imprecise. It is not too imprecise, but the sources of imprecision are very clearly identifiable, because most of the rules in the calculus, in this list, most of the rules are in fact precise, exact. So the place, so for example, this even this rule here is precise. If we consider NPL's Q to be non-deterministic choice, but here the source of imprecision, of course, is not here. It's the fact that real programming languages don't look like this. They say if C, then P, else Q. And so, although, yeah, this is something I skip, but I'm going to show it now. But I promise it's not very long. Yeah, of course, I have to find it. Will go. Right. Let's consider the following case. If n is greater than n, when we assign x, when we assign y to x, else we assign z to x. And then we do n receives n plus 1. And then if we do n, if n greater than n, and t receives x. Now, what you can see here, because you all have very high mathematical education, is that if n is greater than n here, the first time around, and we increase n by 1, n is again going to be greater than 1. So in theory, we have 4 possible paths, right? True, because here we have 2 possibilities, and here we have 2 possibilities. There's no else, but still there's a... So here we either do t receives x or nothing. So in principle, we have 4 paths, right? If we call the first 2 paths, well, we can have true, 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 false, false, true, false, false. So 4 possibilities. But because you and I are very smart, or at least even if we are not smart, we have a very high mathematical education, we know that n plus 1 is greater than m. We know that in reality there's only 3 paths that are possible. The case in which we have true here and false there is not possible. So, but the Alias calculus doesn't know about this, because it only considers then else and not if C then else. So it doesn't take into account this particular this kind of semantics. That's not its goal. The whole semantics, the kind of standard axiomatic semantics does this. But here we just have a very partial analysis of just one kind of property. So here we're going to find that the possible aliases are x, y, x, z. You see the notation, I have not introduced it formally, it's a slide that I skipped. This means x can be alias to y, and x can be alias to z. Okay? And then here, we're going to find that that now x can be alias to t. So as a result, if we start from what we have here, it can be xyt or xzt. But in fact, z can never be alias to t. Because well, I think you see, right? So this is a major source of imprecision, or maybe the principal source of imprecision. It's the fact that we ignore these conditions. And same thing for loops. Yeah.